right, so let's move on to our next analysis, our chi-square. This one is a little bit different from any of the other ones we've done so far, but it gives you a little bit more flexibility in terms of the analyses that you can use on your project data because it can be used on specific sorts of variables. So let's get started. There's a distinction between two general classes of inferential statistics of parametric versus non-parametric statistics. Most of your classic statistical analyses and all of the ones we've learned about so far are what are called parametric tests. So a parametric test is normally going to have some assumptions that need to be true about the population that you sampled from as well as about the data. Things like the normality of the data, things like homogeneity of variance, of a known mean or variance. And typically these are going to be used for interval or ratio based data. So all the ones we've learned about so far, our ANOVA, our t-test, these would constitute parametric statistics. So if there are parametric statistics, what then are non-parametric statistics? These are going to be analyses that can be used when there are minimal assumptions about the data met in the population from which you sampled. So, for example, if you have a very skewed distribution for your data, it might mean that the classic parametric version of the test you'd normally want to do becomes inappropriate to use and would yield misleading results. And often there's going to be a non parametric correlate. Additionally, there are certain kinds of variable types that render a certain analysis impossible to do. So, for example, if you have a dependent variable that is on a nominal or categorical scale, you wouldn't be able to use your classic analysis of variance or t-test, right? As mentioned, ANOVA and t-test need your dependent variable to be on a quantitative interval or ratio scale. So whatever you do, if you want to, for example, look at the relationship between multiple categorical variables, well, none of the analyses we've learned so far would enable you to do that. In that case, there will likely be a non-parametric version of an analysis that will be appropriate for use. Now, if there is a way to use a parametric statistic, it is typically recommended that you do so because it's a little bit harder to achieve significance with your non-parametric test. The bar for significance is typically a bit harder to clear to take into account the minimal assumptions that need to be true about your population and about the data that you sampled. So if there's a parametric version of a statistic that you can use, it is typically preferable, but there are certain cases when you are forced to use a non-parametric version of a statistic. So for example, your chi-square analysis that we'll be discussing today is an example of a particularly useful non-parametric statistic. So the heart of your chi-square is about evaluating observed versus expected frequencies for categorical based variables. So this is going to be an analysis that's going to work when you are interested in doing some analysis with categorical variables. So if you have categorical data, the idea is that you can evaluate frequencies, right? You could just evaluate how many people fall into various categories. But what if you wanted to actually figure out whether or not there was significantly greater representation in one group versus the other? How would you do that? Well, this is your one-way chi-square. So when is a one-way chi-square appropriate? This is typically going to be a test that is useful when you are currently contemplating a single nominal variable and the actual data is going to be counting the number of people that fall into the various groups within your nominal variable. So a categorical variable, again, as we've learned, that's basically going to be data where your participants fall into one group versus the other. So if you're thinking of a single nominal variable that has X amount of levels within it, and you're counting up how many people fall into your various levels, this is the sort of data where it might be appropriate to do a one-way chi-square test. So what does the chi-square test actually do? If we're dealing with a one-way chi-square, also referred to as a goodness of fit test, the basic question that you can ascertain by using your one-way chi-square test is whether or not there's a quote-unquote good fit between the actual data that you have and theoretically expected data representing the null hypothesis. So what it in effect asks is whether or not more people fall into one level or the other. One thing to note is the one-way chi-square test is denoted by your Greek letter chi square. So that x square, that can stand in for your chi-square test. It's sort of like a fancy looking x, but any of you who are familiar with Greek notation are likely familiar with what the chi letter looks like. Now that's going to be our notation for our chi-square test. So nonparametric tests can sometimes have some minimal assumptions about the data that need to be met, just indicating when the test is appropriate. So for example, the usage of a one-way chi-square test is appropriate when the categories or level within the variable are mutually exclusive. So all of your participants can only be counted into one level or the other. Additionally, you need to clear basically a baseline sample size in order to make the usage of the chi-square appropriate. The expected frequency in each of your levels or cells needs to be at least 5 participants. So basically, you get around this by just making sure that your sample size is sufficiently large to ensure that those expected frequencies at least clear a certain bar. So I'll show you an example of what a one-way chi-square valuable chi-square analysis would look like. Um, this is my favorite hypothetical example of all of my goofy examples throughout the semester, because I always ask students at this point what their favorite kind of music is and what their favorite bands are, and I am always met with blank stares. Now, given that I can't see any of you, I can't enjoy all of your blank stares at the example I'm about to describe, but I would love it if any of you would let me know, what music do you listen to? I love music, I love going to shows. Um, I just am so curious of what people your age listen to, because really, I have never had an experience where I pose this question to a class and people actually give me a straight answer. So email me your favorite band. Dying to know. Now, my example. Let's say, for shits and giggles, I'm polling 21 fans of hard, heavy metal to pick their favorite band. Maybe I'm at Ozfest. Likely not in 2020, but maybe next year. Maybe next year I go to Ozfest and I take a short poll asking 21 fans their favorite metal band. You're likely going to get some of the classic um, best heavy metal bands of all time. Black Sabbath is a big one. Motorhead. Shout out to all you Klimster fans. Maybe though you get a couple goofballs who say that they're new metal fans and their favorite band is Limp Bizkit. Again, I'm guessing that you are sitting there with a blank stare, but unfortunately I can't enjoy your blank stare. I will tell you though that if you were to get on Spotify and look up Limp Bizkit, check out the song Break Stuff. Just to give you some insight into my life, that is my go-to karaoke song. Just letting you know. All right, so what basically would my data analysis look like? Okay, your one-way chi-square test, as I mentioned, is going to be where you evaluate obtained frequencies against theoretically expected frequencies. So your obtained frequencies are just the results of your poll. How many people indicated preference for Black Sabbath? How many said Motorhead? How many said Limp Bizkit? You can imagine the results would probably look a little bit something like this. Black Sabbath is going to be a favorite, Motorhead's going to be a favorite, and you got some outliers there. You got a couple Limp Bizkit fans. So the basic idea is that the frequency outcomes in the different groups are different, right? Not all the levels of the frequencies in the different levels are the same. So, what the chi-square basically lets you analyze is whether or not these differences in the frequencies are minimal enough that they could just be due to chance, just a little bit of like a sampling variability, or is it the case that the differences between the frequencies are large enough that it indicates a true difference in preference? So we need to set up our null hypothesis. Basically, the null hypothesis, unless otherwise stated for a one-way chi-square test, is that all options are equally preferred. That is to say that representation in the various levels are going to be roughly equal. So what we need to do is compile our expected frequencies that would result from this null distribution. So you would expect, if this null hypothesis were true, that there would be an equal number of Black Sabbath, Motorhead, and Limp Bizkit fans. Basically, that the cell frequencies would be the same for all of them. So we're going to need to compile our expected frequencies. We already have our obtained frequencies, F sub O. The idea will be evaluating the extent to which our observed frequencies deviate from expected. Again, you might get some differences from expected in observed that aren't due to a genuine difference in representation in the different groups, just random fluctuations. But if the differences from observed to expected are large enough, we can conclude that there are significant differences in representation in the different categories. In this example, there are differences in preference. So the basic way to determine the expected frequencies that would reflect this null hypothesis, it's very easy. You just figure out what expectancies would have equal representation in the different groups. So it's as easy as adding together the observed frequencies and dividing by the number of levels possible. This will give you your expected frequencies that would reflect equal frequencies in all your levels. So if preferences were equal between the three groups, we would expect frequencies to be 7 in each of the groups. Okay, so obviously our observed frequencies differ from these expected frequencies, but the idea of the chi-square is evaluating whether or not that difference from observed to expected rises to the level that we can conclude that the differences are due to genuine differences in preference as opposed to random fluctuations. Okay, so in general, unless otherwise stated, the null hypothesis will reflect that the frequencies in the different cells should be the same. Now, that's not always going to be the case, and I'll show you that a little bit later. But basically, unless otherwise stated, you get your expected frequencies for your one-way chi-square by dividing the total number of participants in your poll over the number of groups within your single variable. So we've seen this notation k before. It's the same here. It represents number of groups. Okay, so n is the total count of people in your sample size. K is the number of levels of the variable, i.e. the number of groups. And the idea is we're going to calculate our chi-square statistic by evaluating the extent to which observed frequencies differ from expected. So this overall chi-square statistic is going to be a single obtained outcome. And the larger the chi-square is, tells us that observed differs more from expected. So this is your basic formula for your obtained chi-square. As you can see, it's going to be a series of figuring out the difference of observed to expected. As you can see there within that parentheses, you know you need to do that first. Basically, you're going to need to go through all of the levels and get the difference of observed to expected, square that difference, and divide by expected. And then you're going to sum up that result for all three of your levels. The reason you can't just sum up the differences from observed to expected is that for some of the levels, the frequency is going to be higher than expected, and for some, it's going to be lower than expected. So, what this formula does is it gets around that issue where summing up the differences by themselves might not necessarily accurately reflect the magnitude of the differences of observed to expected. So, we've seen this sort of setup for an equation before. The reason it's a little bit more complicated than you might think it has to be is because you need to make sure to do that squaring to make sure that you get an accurate sense of the magnitude of the differences of observed to expected. So that's your basic formula for chi-square, and this is what your computation would look like. Again, that first part of the formula is getting that observed minus expected, squaring that, and dividing by expected. So as you can see, you just go down the line and you run that computation one at a time for your various groups or levels. Then from there, you just sum up those different values that you've computed, giving you your overall obtained chi-square value. So chi-square for this example equals 8.85. You then evaluate for significance. So as always, we've got our critical chi-square table. You need to get your degrees of freedom, and you need to figure out what your critical probability value is. So you use the table similar to how we've seen before. So our p-value, unless otherwise stated, just use that p equals 0.05 column. And then your degrees of freedom for your chi-square, going to be, in this case, k minus 1. So there were three levels. So k equals 3, minus 1 is 2. So your degrees of freedom for this particular example is 2. P equals 0.05 column indicates that our critical chi-square value is 5.99. So, is there a significant difference between observed and expected? As always, you evaluate your obtained chi-square and you compare it to your critical chi-square value. You've got your degrees of freedom that helps get you your significant critical chi-square value. So in this case, what we're evaluating our obtained result against is a critical chi-square 5.99. We have exceeded that chi-square value, and the difference is significant. Once you have a significant chi-square, interpretation would basically have you revisiting the actual obtained frequencies and figuring out where that difference was derived from. You can additionally do that by returning to this step. And these values over here to the right, the larger those values are, indicates greater deviation of observed from expected within each of those levels. So you can see the greatest difference from observed to expected is in that second cell representing the Black Sabbath group. So the amount of Black Sabbath preference greatly over exceeds expected. The second biggest difference is due to an underrepresentation of Limp Bizkit fans in this particular poll. As you can see, the difference of observed to expected is also quite great for that group as well. So in interpreting where the significant chi-square comes from, I would revisit this step and see which observed to expected row has the biggest discrepancy. And then basically your interpretation should, as always, just put your results in terms reflecting what the variables themselves are and where that significant result came from. One thing I'll note is that your chi-square value should always be positive. There's no such thing as a negative chi-square. As mentioned, the equation is set up such that even though some of the differences of observed to expected will be positive and some will be negative, that squaring gets rid of the fact that the sum of the differences themselves might not accurately reflect the overall differences from observed to expected. So if you have a negative chi-square value, you did something wrong. Revisit your math. Okay, so we tested our obtained frequencies against a null hypothesis that reflected equal frequencies between the groups. Now, it's not necessarily always going to be the case that you're theoretically expecting all of the groups to be equal. So let's say, for example, you are interested in mapping your sample polling data against maybe national averages. So the example I'll show you will reflect a question as to whether or not a sample of undergraduates reflect political affiliation breakdowns from national based data. So let's say I were to collect polling political affiliation data among maybe a typical undergraduate classroom, maybe in Fargo, North Dakota, where this data came from. You would anticipate the breakdown of political affiliation of people affiliating as Democrat, Republican, or Independent would look a little bit something like this. That would reflect the typical conservative, independent bent of your undergraduate population in North Dakota. Let's say the question is not, is there a significant overrepresentation of one of those groups? It's, does this classroom map onto national political affiliation breakdowns? So if you follow Gallup polling, which updates approximately every 2 weeks in the United States, you don't necessarily expect that political affiliation breakdown at a national level is going to be equal. Depending on current circumstances, the political winds blow and change the extent to which people identify as one political affiliation or the other. So, for example, at the time that I compiled this problem, the affiliation breakdown in the United States looked something like this, with a roughly, or not roughly, an exactly equal representation of Democrats and independents, and a slight dip in Republican affiliation. The question in this case is, does this undergraduate classroom map on to the national affiliation rates? The national affiliation rates are inherently not the same in the different groups, right? 36 represent Democrat, 36 independent, 28 Republican. Those groups are not equal. The idea is, what would my expected frequencies for my North Dakota classroom be if they reflected this inherently not the same in the different groups breakdown? So the process of getting your expected frequencies will need to reflect the fact that we're not expecting the same number of participants in each of our groups. So, in asking if the distribution of the undergraduates is the same as the general US population, I need to take those proportions from the national data and I need to apply them to my actual sample. So, if I was to expect my classroom to reflect those national averages, I would just take those percentages and apply them to my N of 75 from my classroom. So, in this case, you would expect the frequency for the Democrat category to be 27 participants, so on and so forth for my other levels. Again, this is just me compiling my expected frequencies based on those Gallup averages. And again, I'm just applying them to the actual sample I have in front of me. So I take those percentages and I apply them to my actual sample. Thus, my expected frequencies will reflect the fact that I am not theoretically expecting the same level of frequencies in my different groups. Then from there, once I have my expected frequencies, the process of computation is the same. It's about evaluating the magnitude of the difference of observed to expected in my three different groups. So the computation of the chi-square is the same. You do that observed minus expected squared over expected for my three different groups. And then same as before, I just add up all of those values I got, giving me my overall obtained chi-square. So for this particular data, the overall chi-square is 4.76. Once again, evaluation for significance. Your degrees of freedom is going to be k, or number of levels, minus 1. So again, my critical chi-square is 5.99. Does my obtained chi-square exceed the critical value? In this case, no. My obtained chi-square of 4.76 does not meet or exceed the critical value of 5.99. This is a non-significant chi-square. Thus, what we conclude is that the distribution in the class is roughly the same as the expected frequencies derived from the national data. Now, as mentioned earlier, the chi-square test, being a non-parametric statistic, is a pretty weak approach for analysis. What that means is that it's kind of hard to detect differences that might be there. The bar for significance is just pretty high to take into account the nature of this data. Now, if you were to go back and look at the observed versus expected frequencies for this data, you might say to yourself that it does appear that the classroom is different from expected. It does appear that there's much more representation of Republicans and independents in the North Dakota sample than you would expect from the national averages. This is what I mean by the chi-square being a relatively weak analysis. It's not able to show you that these differences are significant. You need more extreme differences of observed to expected to rise to the level of significant for your one-way chi-square test. Okay, I'm going to show you a practice problem. I'll explain the setup, and then I would recommend pausing this video, taking some time to work on the practice problem, and then coming back to the video to see if you did it correctly. So let's say I'm surveying a series of Miami undergraduates on their favorite psychology class. A number of people indicate that their preference is social psychology, a number indicate their preference is developmental psychology, and relatively fewer indicate a preference for neuroscience. So basically, just collect your expected frequencies for this particular data, calculate your overall chi-square value, and evaluate for significance, and come back when you complete that computation to see whether or not you followed along. Okay, if you're returning to the video, now let's go through and make sure that we've worked on this chi-square practice problem. Okay, so in order to get your expected frequencies, you basically take the sample size for your observed frequencies and divide by the number of potential groups, getting you your expected frequencies reflecting equal breakdown between the three groups. So we have our observed frequencies, which is just the obtained data, and our expected frequencies, and we calculate the magnitude of the difference between them. So the calculation of your chi-square involves you going through each of the levels one at a time, observed minus expected squared over expected, and run that calculation for each of your levels. Again, the magnitude of those values tells you the extent to which observed differs from expected, with the greatest difference being for the neuroscience group, with what it appears to be fewer people than expected, indicating a preference for neuroscience. But you need to evaluate for significance by evaluating your obtained chi-square against the critical value. Again, degrees of freedom for your one-way chi-square is k minus 1. So it's the same 5.99 critical value again. And in this case, our obtained chi-square does not rise to the level of significance. This tells you that your observed preferences do not significantly differ from expected. So again, this demonstrates the quote-unquote weakness of the chi-square test. It did appear by just eyeballing the frequencies that maybe that underrepresentation of neuroscience would drive this to significance, but the magnitude of the differences was not great enough to reach the bar of significance. What this tells you is that the chi-square needs to see substantial differences from observed to expected to rise to the level of significant. Okay, so I'm going to pause it there and pick back up with our two-way chi-square.